Let's apply our knowledge about beams and the beam element in the case study of an auto haul trailer. These are trailers that have an open framework type of structure, and many of you have seen them lumbering along the highways of your country. Some cars are delivered from factory to the show place in these trailers. Others are delivered in closed box cars, which gives a little greater protection. For our auto haul trailer, I'll discuss the general problem and show how the automobiles are carried on these trailers. We'll do an analysis of the sidewall, which is a strictly frame structure, and in particular as it would be used in rail situations where it's loaded on a flat car. Then we'll study a component called the kingpin, which is a means of capturing the trailer and attaching it to a truck tractor, or on the rail situation, a stanchion on the rail car. Auto haul trailers are made typically of cold rolled steel tubing. There are some that are made out of structural steel shapes such as I-beams and channels that are hot rolled, but everything we'll deal with here is cold rolled steel. A major manufacturer of these kinds of trailers is the Traffic Transport Engineering Company of Romulus, Michigan. Their president is Bud Stewart. Now, this company came to me and asked me to help modify an existing design so that it could be used for rail car use. And the application was to go from San Francisco to Los Angeles and back. And the manufacturer had a factory in each city such that it could be a unit train loaded fully in both directions. That would be a rather nice application. Let's take a look at the concept of the kingpin and how it attaches to a stanchion on a rail car. Here you have a rail car, and there are two stanchions illustrated by these lines. And there's a kingpin in the front part of the trailer, sometimes called the apron plate, that will be essentially grabbed by the stanchion and will hold the trailer on the rail car. They're usually loaded in pairs as shown here. Also with the lowboy trailer sketched below, made of the structural shapes, you have a similar situation. Now the purpose of the lowboy trailer might be to haul mill van containers on the left, or perhaps partially assembled vehicles on the right. I have some photos of the loading process for the trailers. Here you see a large gantry loading the trailer onto a flat car. Now in this case the trailer is empty just for practice. One thing you might worry about for a loaded trailer though would be whether you might get some bowing of the trailer end to end that would then catch on the bottom of the rail car, let's say, so there's a bit of a clearance problem here. Another thing would be the stresses at the attachment points, which are at the four upper corners on what's called the rail of the trailer. And you can see the scale by seeing the little man here. Here are two more photos of the loading process. The upper picture showing the loading of a filled trailer on the left onto the flat car, and then the bottom picture showing the loaded rail car with two trailers. I had always wondered how these automobiles were being held in place, and the system is reliable and simple. The automobile itself here is carried in tracks that support the wheels. The tracks might be a channel shape shown here, or they might be a more of a Z section such as this. Anyway, over time these tracks have been used for many trips over the highway, and so the tracks are pretty well proven merely by that field use. Now the support of the tracks themselves, though, is done by various linkages and pivots using pins. These tracks are pinned often to a vertical member, shown here, where I show a pivoted track, pivoted perhaps with one end on the bottom rail and then the other end brought into alignment so that you can pin to the vertical member. And the system is intentionally made statically determinate, and that means that if you pull one pin out on a side, that the system will collapse. This is done intentionally, as I say, because if you ask the driver to position 2 pin holes, that in general is not possible after these structures are out in field use and all bent up. Now once the automobile is driven onto a track, then a hydraulic jack is brought into play and used to raise the car. But after the automobile is lifted into place, then the hydraulic pressure is released so that during its travel over the road or on the rail car, you'll find that the automobiles are completely supported by their pinned tracks and not by any hydraulic pressure. Some of the automobiles are done as shown here, where they're raised up and then a pin through a hanger up here locates it with respect possibly to the upper rail. Now, when it came time to model this system, I knew that I had to position the center of gravity of the automobile and make some sort of a rough caricature of this suspension system. Now, since I wasn't interested in the track itself, I merely used rigid bars shown here and here, and then those are given a stiffness that's substantially greater than the surrounding structure. There was a firm connection at the center, so these were not hinged. They were, in fact, then a pair of bars welded together, you might say, but then with moment releases at the ends to represent the pins. Often I would model the link, which is hanging here, as if it were a rod then rather than a beam element, so that it would have automatically a moment release. In my first study of such a trailer, I used a model of the rear suspension that was a little bit oversimplified. I basically pinned 2 locations where the wheels attached at the rear of the trailer and turned it into this kind of a roller connection. But if you notice, what that does is to hold rotations 0 at the, roughly speaking, the rear end of the vehicle. And that really is an over-constraint. The trailer, in fact, can pitch up and down on the air springs. There are some time constants involved, and it depends how rapidly the loading is applied. But later I decided it would be more appropriate to model it as a wiffle tree, shown here on the right, where now you allow rotation, but the gross vertical motion is constrained. So, depending on the details of the pneumatic suspension, either the left or the right model might be appropriate, depending on how quickly air can be transferred from one pneumatic bag at the first axle to the second pneumatic bag with the second axle. I think the effect was local in the sense that when we did restrain, as shown in the left diagram here, this tended to cause some high moments in the model just forward of the suspension. Whereas I think there would be more moment relief than that in the actual case. So subsequent models were done with the wiffle tree. Now the loading that you encounter in use could be of 2 kinds. You could have the conventional over the road, and by that I mean as a highway travel case, or you can have the rail car travel case. Now, the over-the-road loads were pretty well understood already from past use, so I didn't have to get into that. But the railcar loads are specified by the American Association of Railroads, and they have a standard on field impact tests for loaded open-top cars. And this would have been developed for other freight in general. The loading criteria that were established by the American Railroad Association were dynamic in nature. They had to do with impacting a loaded rail car, such as we're interested in, against a parked gondola car full of limestone. This accident, you might call it, was meant to represent the coupling of rail cars in the rail yards, and so it was viewed as one of the more severe loads. But it's made somewhat extreme by requiring this be done at 4 miles an hour, 6, and 8 miles an hour. Furthermore, such that the rail car in question, which would be our typically flat car with 2 auto-haul trailers on it, had to be coupled both forward and backwards into that gondola car. Now, as a design engineer, you would be worried about converting these dynamic loads into something static, because we need to get something like a stress that's expected from this. When I first talked with the sponsor of this analysis, I told him that to do a full dynamic study would be a $50,000 or $100,000 study, but that static equivalent cases could be done much, much cheaper, on the order of thousands of dollars, a couple thousand. And so they were quite enthusiastic about getting a static equivalent. I thought in my mind then about what would be a static equivalent set of loads, and I had done some work with the Air Force on crashes of transport airplanes that carried cargo primarily, and the Air Force had originally required an 8G fore and aft hold down requirement for all of their pallets and the heavy equipment that would be constrained on a set of rails within the bay of the aircraft. And then they found that that was overdoing it, that there were no survivable accidents between 5 and 8 Gs, and so they lowered it to 5 Gs. So going into this automotive and rail type application, I had in the back of my mind that 5 Gs was all that a military organization had decided was necessary, and that was for survivability primarily of the crew, so that the goods wouldn't break free and crash into the people. I came up with a number of 2 Gs then as what I thought would be the most severe loading that one should apply in this case, and essentially felt that qualitatively that was similar to the American Association of Railroads standard that applied. So this table shows then that I decided to put a 1G corner lift case to represent the loading of the trailer onto the rail car, and then sitting on the road it would be subjected to 1G. That'd be the conventional over-the-road load. Then the 2 coupling tests could either be forward or reversed loading upon the impact with the gondola car. And lastly, we should look at some combinations of the 1G downward and the 2 Gs, either forward or back. Now, it soon turned out that the worst case would be 1G down and 2 Gs forward, just because of the way the trailer is attached, and I'll show that in a minute. Let's look at the finite element mesh that was developed for the sidewalls. First of all, there really are 2 sidewalls separated by some distance as you view, say, from the rear of the vehicle. Then you should, in principle, study the whole vehicle with a left wall and a right wall. But using a St. Venant idea that those kinds of small differences in member locations will gradually disappear as you move away from the point in question, I decided to really analyze a trailer made of 2 left side walls and then a trailer made of 2 right side walls, and then we could take the worst case. Now, the big difference in the 2 walls was that the member shown here was moved over to this position on the right side. Now, up above you see the empty trailer, whereas in the bottom figure I've shown the tracks that support the 7 automobiles. And I'll just sketch the centers of gravity then of those 7 automobiles to give you some feeling how they're moved around the trailer. Well, after seeing this design, I complimented Jim, who was the draftsman designer for the sponsoring company, and I said, boy, you really must have to work hard to figure out where to put all these members, because I sure wouldn't have guessed this pattern. And he says, oh, no, it wasn't that bad. He said he just put the holes located so that the driver could get out of the car by opening doors on either one side or the other. And so it turned out the positioning of the members here was worked out historically so that a given trailer could carry perhaps 3 kinds of automobiles. Maybe a pickup truck, a 4-door passenger car, and then a 2-door passenger car. And by the time you located members to allow people to get the driver to get out, you had such an intricate pattern. My early runs on this project were done with SAP 6, and then later on this project and on other projects I did use MSC Nastran. But actually any of the commercial codes would give exact answers, because the simple beam element, when it's only exposed to end moments and loads, is precise. So in this case, we had beam elements that were as long as 8 feet. And so although people get used to thinking of finite elements as being small, these were definitely not small. So this was more like a conventional civil engineering frame structure. When we got the results back, I plotted the undeformed position with the dashed lines and then the deformed position with the solid line. Now, initial runs in showed some droop of the belly of the vehicle, but not bad, 4/10 of an inch. The stresses were not bad either in the case of this corner lift. What we've done then is to lift this body at the attachments at the upper corners of the upper rail. The stresses that were the highest were located just outside this triangular region here, which acts as a rigid inclusion, as does the one back here. And so you soon learn that, gee, if you're going to have a flexible structure and you embed a very rigid triangle in there, that you're going to have stresses that are pretty high just outside of that rigid region. So some reinforcement had to be done here in the way of fillets and so on. But this particular solution was not very high stressed and was not felt to be threatening. The front impact was a little more severe, in which you again got belly droop of about 5/10 of an inch, and as shown. Now this is prior to the reinforcing and the strengthening of this region here. If you look at the trailer then that has both this impact plus the normal 1G loading on its wheels, you'll get the result shown in the next figure. So here we show the combination of loads, and this is the most extreme case where you have front impact and then you have the over-the-road gravity on the wheels. Notice that this is the original model that restrained rotation at the rear end and made the suspension area translate rather than possibly allow some moment relief of this structure. One thing we should comment on, since this is the worst case, is that the members do show quite a bit of bending. Notice this member here, for instance, and likewise other members as you go to the back here. The way that this trailer used to be analyzed before we used finite elements was by a classical method assuming that the entire side acted as a single Euler-Bernoulli beam. In other words, plane sections remaining plane. Now, that's not really appropriate, but that's the way the original sizing was done. And you can certainly see that plane sections do not remain plane. Neither is there good shear coupling between the top and bottom rail because it's only held by these rather slender members. Here are the results for the second combination loading, namely the normal 1G gravity load when the trailer's on its wheels, plus the rear impact due to the coupling of the rail car with the gondola car. And there's a fortuitous cancellation of effects here, such that there's very little bowing of the belly of the body, and the stresses turn out to be much less severe than for the front impact case. So it's a surprising thing to me. I hadn't anticipated this, although in general I try to anticipate what the answer should look like. The reason that there is some cancellation is that the stanchion up front then, in this case, is putting quite a large load in the forward direction, which tends to stretch the trailer, as opposed to the rear impact, which puts the trailer under compression and makes it droop. Let me summarize some results for our sidewall project. First of all, the deflections were acceptable, although they ranged as high as 9/10 of an inch in the belly droop. That really isn't a lot considering how long the trailer is. Some manufacturers have built a pre-camber into the unloaded structure such that when it's gravitationally loaded it then straightens out. But that's not needed for such a small droop. A high stress region was found in one of the front members of the trailer and corrected. Then a high stress region was found near the triangular stiffener area up near the top rail at the front of the trailer, and that was corrected. Another high stress situation was an eccentric joint where this member to the left and the member to the right are transmitting forces which affect the intermediate region shown here in red. If that joint were merely aligned as shown over here, then the vertical member would have very little moment induced. Of course, there can always be three-dimensional effects in thin-walled tubes, but just arguing this from the Euler-Bernoulli beam theory should be adequate. Now, all of these observations about deflection and stress depend on the original assumption that we were designing to a 2G impact situation. That's a reasonable number, and it can be shown even more so if you look at the overturning moment on the vehicle. You find that at 2.7 Gs, the trailers will in fact flip end over end about the kingpin restraint. As they're mounted on the flat car, they really are not clamped at the rear. They're free to roll on the wheels. So it wouldn't make much sense at all to design these vehicles any higher than 2.7 Gs, and even that seems like a very, very, very severe sort of an incident. And so I think the number of 2 Gs is probably about right for this situation. I'd like to continue our case study with a side issue here. This is a case of the kingpin and the stresses in it and the plate around in its region. Now the kingpin is a beam-like structure in terms of the pin region, but it's also got a cap on it or a head that's plate-like, and the plates around it are crucial. So we're pushing you a little bit on going into a hybrid structure here. Here's the kingpin cross-section. It's a very, very strong device. It's made out of forged steel, supplied by a vendor, and typically never fails to my knowledge because they're made so tremendously strong. However, when you put that into an assembly as shown here, you've got the problem of capturing it, and generally by welding it into thin surrounding sheet metal. Now, I'll show that assembly in the next figure. Now here's the figure showing a cross-section with more detail of how the kingpin is welded in. What they do is they have this plate, sometimes called an apron plate. Anyway, this is a plate that would rest on the truck tractor, and this system's called the fifth wheel system. They flame cut a hole here for the kingpin, so it's kind of a rough cut. And then in the original over-the-road models, they welded with a fillet weld in this region and in this region. Because we were worried about higher possible loads in the rail car situation, immediately I told them they should start welding at these other locations if possible. Now, I mentioned here that the head of the kingpin is plate-like and the shaft is beam-like. We really are not interested in the kingpin because that's supplied by a vendor and it's already been field tested many, many times, so that's okay. The loading cases on the kingpin involve the previous one by the American Association of Railroads, which was a dynamic one, but there's a separate Society of Automotive Engineers standard on fifth wheel kingpin performance that specified that you should be able to withstand 210,000 pounds here. And that turns out to be more critical, certainly more critical than the 2G load that I was using as a static equivalent, because the entire trailer times the 2Gs came nowhere near this 210,000 pounds. So I assumed then that the SAE standard was the critical one. I accepted this challenge to model the kingpin area with some trepidation because I'd never even seen a kingpin prior to this. And I knew that the structure was a little bit complicated and not just a simple beam structure that we've already seen. How do you model such a cross-section as shown here? Well, I wanted not to have to model the tubes as full plate structures, although that's done a lot in the passenger car business in Detroit, where sometimes it saves labor to go ahead and do that, even though it requires more degrees of freedom. I was somewhat computer limited at the time, though, and decided then to take the centroid of the stiffeners there, which are longitudinal stiffeners as shown, and position those above the plate structure through the use of some standoff stiffeners here. Now I made those standoff stiffeners relatively rigid because I wanted this beam support here at the left to pretty well restrain the plate that lay under it. Then we did model the plate itself with conventional plate elements shown here. These were four-noted quad fours, you could call them, plate elements. The head of the kingpin was modeled with plates, the shaft with a beam, and then the actually the round knob at the bottom was modeled with plates as well. The baseline design for the kingpin region was modeled, and here's the mesh. One thing that I did have to do was to divide the loading and the reactions in some appropriate way. Now there is a reflective plane of symmetry which is longitudinal. Then I've taken half of the live load and applied it at the kingpin. That was relatively easy. But the isolation of this small part of the total structure had to be done by making a cut at some point rather than carrying the model out over the total system. So I made a cut of the body along these lines, and then I inferred through qualitative reasoning that I would react most of the force shown here and then a smaller amount shown here. Hopefully, again, St. Venant will come to our rescue, and if I've made a bad decision on that, we'll soften the results as you go to more remote points, which hopefully the kingpin is. The stresses then that were found after the first run came from such a deformation field, and we did get 140,000 psi, or 966 megapascals, in the plate just off the head of the pin. And so again we have this problem of a very rigid structure embedded in a more flexible structure, causing high stresses right as the rigid structure stops and the flexible structure starts. Upon seeing how high the stress was in the apron plate, I asked that we do some reinforcement in that region. So a second design involved a longitudinal bar welded over the head of the kingpin. There's an open plate area in here, roughly bounded by this region, and then with the kingpin at the roughly the center of that region. That also turned out to be highly stressed and required another redesign. A third design was then proposed, and it had several bars over the head of the kingpin in the longitudinal direction. I've sketched the deformation field here. And again, you see this problem that although you can stiffen the body locally, then there are high stresses as you get to the edge of the stiff region and enter the more flexible region. And the stresses still were too high in this case, and were still around 100,000 psi. Now for mild steel that was used here, that was still way too high. A fourth design was proposed. It had 3 longitudinal bars plus a cover plate that covered the entire region. Here's a sketch of that situation, and by now we were asking that there be weldments, a fillet weld here at the base of the kingpin and the apron plate, and that there be welds on all sides of these reinforcing bars. Now some of those were difficult to do because these longitudinal reinforcing bars were hidden under the cover plate, but nevertheless they were able to blow through and fill that area in. So we just completely welded everything we could see and some things that we couldn't, and covered it with this relatively heavy cover plate that spanned the area out to the conventional reinforcing tubes nearby. Let me show a top view of the same kingpin region. Now the cover plate would be hiding this, but under it will be these longitudinal solid members, and then the kingpin itself. You can see the head, and you can see that there's not that big a amount of apron plate exposed now here. This reduced the stresses, we believe, substantially, and that was not proven analytically but proven in field test in California later. A fifth design was also proposed but was neither analyzed nor built, but I'll show it just for completeness, that this also looking from the rear toward the front shows large steel tubes now that were brought in nearer to the kingpin head, and then a doubler on the plate such that you would weld that in and effectively increase the apron plate's thickness by a lot, and then would completely weld as before. I believe this also would have been adequate, but didn't have quite the depth and the carry-through strength that the fourth design did, and was therefore chosen. Our design study of the kingpin area was very useful. We showed that a redesign was needed and came up with some suggestions for new designs. An analysis of the final chosen design, number 4, was not done because the proof was to be carried out experimentally. Another thing about the process was that we appreciated the difficulty in capturing such a rigid component as a kingpin by relatively flexible plates. We were pleased when the vendor for this kingpin started a new design and released a new design that had a flange integrally forged into the head such that you could now more easily capture with some cover plate the kingpin. I can say a couple words about the field tests. These were done out in the deserts of California by the Southern Pacific Company, and the flat car loaded with two 55-foot trailers was rolled into a parked train which consisted of gondola cars with rock in them. So this was essentially the extreme test of the flat car rolling into an immovable object practically. The tests were done at 4 miles an hour and 6 miles an hour, and some dust was raised and some commotion, but the trailers held up. And this was an ultimate test in that the goal was only to make sure that the trailers retained their structural integrity and didn't break apart. The third test was to have been done at 8 miles an hour, but it was done with more enthusiasm than that. Apparently as much as 12 miles an hour was registered, and the trailers crashed into the parked train, and there was a lot of rattling and dust and breakage of some windshields from the old used cars that they used as test automobiles on the trailers. But the kingpin area held intact, the entire trailer held intact, and that was the proof of the final redesign. Now, those trailers were 55-foot trailers, and they were used in a test situation on the West Coast for several years. The ultimate situation was that these would have had to have been made larger due to changing highway laws, and that project was held off, and to my knowledge the fleet of such trailers was not put into production.